Okay, so we're continuing with lecture 45, ideal gas law. This actually was fortuitous because when I was looking, this is just the last problem, and I was trying to go back to the information from problem 3, and I think it would have been a little more confusing than rewriting the problem as I have here. Now, what this problem is asking is a sample of uranium hexafluoride. It's more likely to have something like an unknown here, and they said they have a density of 12.7 grams per liter. What is the molar mass of uranium hexafluoride? Well, you could certainly go to the periodic table and figure that out, but if it's an unknown, then you couldn't, of course. So that's more likely what you'd see in this case, but it's nice to be able to go back and check. We know that it's 352 grams per mole for uranium hexafluoride, so that'll be a nice check. But if you're given a density and then this other information, you start with the ideal gas law. Now what we're going to do is we're going to determine the N, the moles per liter. And you see we have grams per liter. I'm not going to write out the number, but we'll figure out the number of moles, and we'll use 1 liter as our volume again. So, and then we can find moles per liter. If we invert that, liters will cancel, and we'll be left with grams per mole. So it's really, if you look at what we did for number 3, you'll see that this is working backwards on that problem. To get the molar mass, whereas we used molar mass to find the density before. So again, you might say, well, why should we do that if we know we can just look in the periodic table? Well, if it's an unknown that you're given, then you won't be able to do that. If you're given the density and this information, you'll be able to backtrack to the molar mass, and here's how we do it. So we want to find N, so PV or RT. The pressure is 0.915 atmospheres. The volume is, I'm going to say 1 liter, just like we did in problem 3. Earlier problem, we get to pick that value. The temperature is 308, so it's very similar to the problem that we did earlier. Atmospheres, liters, K. And we end up with, and I could just use the information from the previous problem, but I'm going to work it out again here. And we end up with 0.0362 moles. Now, so the density, or I should say the concentration here is going to be 0.0362 moles per liter. I could say 1.00 liters. So that is going to be our concentration. Now, if we knew the molar mass, we could do like we did in problem 3 and convert this to grams per liter. We're going to assume that we don't know the molar mass, but since we have the density given up here, we just take 12.7 grams per liter. We take this as our conversion factor. We flip it. Liters cancel, and we're left with 12.7 divided by 0.03562, and this comes up to be 351 grams per mole. It's different. It's 352 is what we calculated from the periodic table. This is going to be slightly off because we did a lot of rounding. Several steps happened, but that's fine. If we wanted to get to 352, we would just had to be a little more, have a few more significant figures. We would have been okay. So if you don't know what the compound is, it's unknown. They give you the density and they give you the information you need for the ideal gas law. You can find the moles per liter and then take the density and divide by the moles per liter, and you'll end up with grams per mole. Now, this is where a lot of students, they use an equation based off the ideal gas law. I'm going to show you how to derive it, because for me, I like to do these steps out and just see what we're dealing with and work with the ideal gas law as is. But you'll see a lot of times that the molar mass, so this is capital M, lowercase m, this is the molar mass. And so capital M, lowercase m, and this is in grams per mole. So this is lowercase m for mass divided by n for moles. And so if we solve for N, bring that over, then it's grams over molar mass will be equal to the number of moles. We plug this in. We have PV, this will be M over the molar mass. And don't think of that subscript as a different variable. That's just how they denote it in your book. If we then rearrange this equation, we end up with P, the pressure times the molar mass, is going to be equal to M over V RT. Well, the mass over the volume, that's just density. So the final equation is this. Now, this will make the equation much simpler because, or the problem much simpler because you can just take the density, that's our D, you have the temperature and the pressure, plug them directly in here and solve for the molar mass. And you say, well, why'd you take us on this circuitous route then, Dr. Champagne? What the hell? I mean, sorry. The reason is because a lot of times students use equations, they have no idea why they work. They don't know where they come from. And I prefer to do out the problem in this form first, just using the ideal gas law, and then once we have solved it using just keeping track of the units of measure, then we can go and use an equation like this. Once you have an equation and you know why you're using it, you know what these units are for each of these new terms, and you see that it is just the ideal gas law in a different form, fine, that's absolutely fine. But having that and thinking of it as a completely different equation, it's not. This is just PV equals nRT in a different form. That's what I'm against, is when people see that these as two different equations. They're not. It's the same equation. And if once you recognize that, if you want to use this, that's fine. I prefer to always do it out from the ideal gas law, and everything's fine. That way, because you just keep track of your units of measure, figure out what you want to have in the end. For instance, when you want to have grams per mole, and figure it out from there. But that is up to you.